let me start by thanking the organizers for inviting me and, of course, organizing this amazing event. So, does this work? No. Okay, I apologize. So I come from the applied side of category theory, and what we do is study systems and processes and transformations. So we usually read monoidal categories representing a situation in which we have objects which are resources and morphism which are transformations. And it's established now that such a thing is the way to represent how processes work. What happens is that often it's not enough to have a transformation between two, like a starting resource and a resulting resource, because this transformation depends on some kind of hidden input or a private choice that we are not allowed to see. So, for example, context, when we deal with programs or natural language, is very important. So the same program can have a different meaning depending on what's the context surrounding it. So like the values of variables in context, or the same sentence can mean different things. Or private state. So if we have a transformation that is carried about by an agent, this agent might conserve a state between executions. Therefore, the same transformation could be actually a family of transformation, which is depending on a state we don't get to see. And in my work, I deal with cybernetic systems. And in that case, what we have is policies or controls or strategies in games. So the same game or the same system can change its own behavior based on the observation they make and some kind of private choice of policy to move in the world. And finally, recently, it was noticed that some process theories have naturally keys or guards to transformations. So in order for transformation to happen, there might be a precondition or some kind of additional resource that we need that is not directly involved in the transformation itself. Therefore, it seems natural to add a third input or a port to a box representing a transformation of process theory. And sometimes even a fourth one, like in the seminal work of KSW, I don't remember the names, I'm sorry. And what happens is when we have this third dimension, we get not just additional ports, but a whole new dimension. You should imagine these blue wires as living above the diagrams we draw on the plane. And this is an additional resource theory that we call M in this talk, which provides an entire new world of dynamics to talk about these preconditions, or the context is that the processes in C actually depend upon. On the other hand, we might have a different way to have a dependency of a process on a third thing, which is the process itself is not known. I cannot observe or talk about it directly, but I am forced to use some kind of proxy description. And this is the second construction I'll talk about today. And just to give an example, oftentimes the space of mappings between two objects is too big. Like imagine smooth maps between two manifolds are an infinite dimensional space. So I cannot directly describe such a map in many cases, especially when I'm dealing with applications. Or the map itself might be not well defined because it's not a map, but it's a probability measure on that. So in that case, we use a third, ouch. In that case, we have to use some kind of proxy space to actually probe the space of mappings. And this acts like a kind of parameterization. So both the two construction I introduced now are things that we have been spending a year thinking about. So at MSP, which is my group, we are daily dealing with Para, which is a construction that we came to know from this paper by Fongspiegel and Tuyera, in which it's used to model learning. And we realized that it's actually very important to have such third dimension to describe cybernetic system. At the same time, Toby's math has been playing with Proxy. So we use this way to model proxy in mapping spaces. And we realized they are related and they could actually be described in a very similar way, and they are conceptually very close. So in this talk, I want first to let you know about these new constructions. And secondly, I want to sketch what this is about, since there's no survey about this construction, despite being already in the literature. And also ask you if you know examples or if you know any way to improve this work. For example, yesterday I already seen in a talk, someone talking about an instance of this. So there's already things happening in the literature which can be captured by these new constructions. And the second thing, I want to apologize because this is new territory for us. So I never deal with higher categories. I'm going to probably say something stupid. So I apologize in advance, and I'll be grateful if you point this out to me and so I get corrected. And third, I'd really love to know what's interesting about this construction in your opinion and how we can improve and continue this work. So the fundamental idea, just to give an overview of what we're going to see, is that, so suppose we have a V-enriched category C, then a parameterized map is a choice of maps from A to B for any given small p in a big P. And there's two ways to do so. The first thing is this mapping that assigns a small p to an f of p is an internal map in C, and the other way is if this assignment lives in V, so the enriching base. And the first instance is what we call the para construction, and the second is the proxy construction. So you see the idea is very similar, but it lives in different, sits in different situations and positions with respect to C. So in para C, our map from A to B is first of all a choice of parameter, which gets attached to the input space, and then a map from P tensor A to B. While proxy is a choice of parameter, but now the parameter lives in the enriching base, and then this parameter picks a space of morphisms in C of AB. And this is very different. So compare, for example, a smooth family of maps given by para and a family of smooth maps. So they can be very different because no smoothness assumption is made on the choice of morphisms themselves. All right, so let's start from para. So the most general way, but profitable way to introduce para we found is starting about from this, oplux and module. So we'll fix for the talk a small monoidal category M or dot J, and we'll call strict left oplux and module a two category C equipped with an action, which given an object in M and an object in C yields another object in C, and same for morphisms, a co-unitor and a co-multiplication. And they satisfy the obvious pentagonal and triangle laws. And I want you to notice that I'm not assuming that this is using the two structure of C. Okay, so I'm not using the two-dimensional structure yet. These are definitions that could be easily given for one category C, but we'll need the two-dimensional structure later. And second, oplux is just because that's what I need in para, but we also need lax and pseudo actions sometimes. So what you have to do is just reverse co-unitor and co-multiplication, or assume that they are an isomorphism. So what is an object like this? This is simply a categorification of an action of a monoid. Okay, so a monoidal category is like a categorified monoid. Category is like a categorified space or set. And this is a way to categorify an action of M or C, all right? So this is what you should have in mind, that M is kind of like a monoid of scalars and C is a left module over M. And the usual case that we deal about is when the action comes from a functor like that. So we have a monoidal functor from M to C, and the action is constructed by first using F to move scalars from M to C and then tensoring it with whatever we have on the right. And this often is the case when, in particular, M is like a Cartesian category and C is a monoidal category, and we have an adjunction between them. But this is not necessary for the construction. It's just like a very common class of examples. So when we have such an oplux M module, we can run the para construction on it. And we got a bicategory whose objects are the same of C, and whose morphisms are, as we've seen before, parameterized morphisms. So for the offset between X and Y is the sigma type we get by first choosing a P and then choosing a morphism from P acting on X and then Y. So the parameter lives in M and the morphism itself is in C. And then epsilon and delta gives us identities and composition, and their coherence laws gives the coherence law for the bicategory. And composition, you can see, is that long string of composition. Is not very hard, but it surely looks nicer when we draw it as diagrams with this third port on. And this is actually what we always use when we deal with such constructions, because the string diagrams for this are much simpler than the category theory written with passing diagrams and so on. Okay, so this is the intuition you should have in mind when you read this. And then we have a two-dimensional structure. So a two-morphism between a pair of morphism with the same boundaries is given by a morphism between the parameters in M and a filling cell which fills this triangle. Okay, so one thing you should notice is that alpha, which is the two cell or the reparameterization, goes in the opposite way. So a morphism from PF to QG as alpha going from Q to P. Okay, and this is motivated by the way we represent such operation in with string diagrams. Okay, you see alpha is plugged on top of F and gives us G after moving along phi. Okay, and so you see why alpha has to go from Q to P. Of course, this is kind of arbitrary anyway, so we could discuss if this is a good choice or not. And of course, when C is a discrete two category, so we don't have two cells actually, so the identities, then phi doesn't exist. It's just an identity. So this becomes a commutative triangle. And let me also stress that, what did I want to say? Let's not stress anything. Let's take examples, okay? So the first example is, this is not something we use, but just to see different things than what we have in literature. So suppose C is the category of measurable spaces or good enough measurable spaces, and M is the category of probability spaces, then probability spaces act by Cartesian product in a sense. Okay, so we forget the probability measure, and then we take the Cartesian product with measurable space. And what happens is that para of this action yields a category of stochastic processes. So a morphism from, say, A to B is not just a measurable function from A to B. We have this additional input of a randomness source, which is a probability space. And then you can use the two-dimensional structures of these blue wires to kind of manipulate these randomness sources. So you could say my stochastic processes, which is a composite of n different processes, is it's controlled by n bits of randomness, and these n bits of randomness have to be used to decide how the different stochastic processes happen. Another example, which is more cute, we could say, is the following. So if C is the metric spaces and M is the multiplicative monoid of the real numbers, then this acts by dilation on the metric spaces. So the action of a number on a metric space is simply by producing a new metric space whose distances are all dilated by that factor. And then if you run para of this action, we get a proof-relevant version of Lipschitz, of the category Lipschitz function. So maps between metric spaces, which are not short, but are allowed to have this Lipschitz constant indeed. And this Lipschitz constant is explicitly chosen for the map. And then the two cells are not very interesting, but allow to refine constants. So you can say that the initial object, for example, of reparameterizations of a given map is the smallest Lipschitz constant you can give for that map. Finally, I have to mention this is the stuff we use para for. So the first instance is parameterized optics. I won't go into this, but if you're interested, it's all in the sources. And this additional direction is anticipated is very important to do cybernetics. And then yesterday, as I mentioned also before, we see the S construction, which was described by J.S. Pacoleme, is an instance of this construction where the acting category is the category subunits of the monoidal category we chose. With the important caveat that in that construction, if you remember, you got just one category. So the reparameterization were quotiented by a relation. And this is the case in many of the examples we've seen so far in the literature. And apart from the last papers we published about the subject, that's always the case. So how did this happen usually? So the first and easiest way to get rid of the two-dimensional structure is to just discretize everything. So you simply forget all the two cells. And you don't know how to reparameterize, you just choose your parameters and you get that. And we're going to use this later on because it's the easiest way to not trivialize the construction and still say something interesting about it. Otherwise, we have a code discretization. So what we take is a quotient along the whole diagram made by M. And this is, for example, the approach by Dalrymple in his paper about dioptics, but we really don't like this because that's a very heavy quotient. Imagine if you have a connected category M, then this is basically squashing everything together and the data of a parameter is almost completely lost. So it's not very interesting. Indeed, what we often found in literature is that we take the same coend, but over the core of M. So the core of M is just the subcategory of isomorphism of M. And so it usually becomes disconnected because you have isomorphism classes. And this makes the data of a parameter not redundant, but like given up to isomorphism. I mean, this is interesting, but the approach that we have at MSP is that two morphisms are really interesting and essential in this construction, especially in the applications we have. So the para construction should really be studied as a two-dimensional construction in which what I call the vertical dimensions of the blue wires we've seen plays a crucial role. And another warning, Spivak also uses a thing called the para construction, which is very similar in the two cells. So if you go to this reference, you see the different kind of two cells. So as I said, we want to use the para construction to produce category laws, controlled or parameterized processes. So we'd like to have another monoidal category. And indeed, this is true. We have to assume something more on our Oplux M module, which is the compatibility of the action ballet C. Okay, so suppose C is monoidal, so it's like a resource theory indeed. Then we need a co-strength, which is a natural transformation like that, satisfying some coherencies as usual, which basically allows us to move the parameter in a useful way. And the theorem we have is that if C is symmetric monoidal and has this co-strength, then the para construction yields another symmetric monoidal category. So we can still use the tensor product there. Moreover, para is not just a construction, it's a factorial construction. This is very, very nice, and there are uses of this fact. So in the literature, we just have very simple statement of this thing, but we can go in full generality and say, okay, let's look at left Oplux and modules, and they gather in a tri-category, which I call the category of Oplux modules with lax transformation. So this is given by, indeed, Oplux and modules. And as one morphism, we have lax linear functors, which are functors equipped with a natural transformation of that kind, again, satisfying suitable coherencies, which is a categorification of the linearity condition on a transformation of modules. And then two morphisms are linear natural transformations, which satisfy that property. And then we have modifications which satisfy another property, okay? So this is a tri-category, that's what we need to know. And then para is a tri-functor from this category to cat, or if we promote Oplux module to co-strong Oplux modules, then we get a two monoidal category. And the most interesting thing is that now if M is symmetric, and if the actions that we look at are not just Oplux, but are pseudo, so the unitor and the multiplication are invertible, then para becomes a two monad over the category of pseudo and modules with lax morphisms. And the unit and the multiplication of this monad are given by the transformation that trivially parameterized morphisms, so parameterized with the unit, so it's like I did nothing, and the multiplication multiplies parameter together. So a twice parameterized map becomes a once parameterized map in this way. And this is still true if, again, we restrict to symmetrical strangle lexical modules. So in the case where we have this tensor product on. Okay, we're done. Oh, sorry. So, all right. Yeah, can I have 1 minute to conclude? So what we have here is that then we can characterize para as a universal property, which is tridimensional. And proxy is its parent, which is constructed like this. So as I anticipated, and the theorem we have is that proxy can be related to para as in the case that either the action that determines by the data we feed to para is closed, or in the case of proxy, if the enrichment is censored. And there's this theorem by Gray and other people that tells that this situation are the same, so we can relate para and proxy in this case. And that's it. Okay.
Are you on my start? So thank you very much. And any question, comment?
At the beginning, you mentioned as examples also functions with state, with internal state. How do you deal with that? Do you have also parameters that are changed when you apply the function? How does this para construction deal with that?
So to deal fully with stateful things, one would need what we call the bipara construction, in which you add a parameter also, like a coparameter in the codomain, and then you did a little bit of Wendy magic to actually make this two parameters dialogue. So there is, I think, a better construction in that paper by Katis, Sabatini, and Walters at the site, in which they do this. And what happens is simply that now you have a fourth port beneath, and you can imagine this to loop up. And of course, you can add morphism, and the whole idea of having a new dimension of dynamics happening is still there.
Thanks for your talk. I have a sort of basic and possibly naive question, which is how does your para construction compare to the notion of actagory?
So what I call an Oplaxen module is an actagory.
Okay.
Okay.
Okay. Do you see any? Okay. If no other questions arise, okay. So thanks again. Let's thanks
Thank you very
again,
much.
Matteo.